Hello everyone, I'm Norman Wildberger, and welcome to this number 6 in our famous math problem series. Today we're going to go back to Archimedes and talk about one of his most remarkable accomplishments, squaring of a parabola. And that's short for calculating the area cut off by a line from a parabola. Archimedes, of course, the greatest mathematician probably of all time, and a prominent physicist as well, astronomer, inventor, and engineer. During his lifetime, he was celebrated probably more for his engineering accomplishments and his inventions than for his pure mathematical discoveries. He lived 287 to 212 BC in Syracuse, which is in Sicily. And amongst many things that he did, he discovered a screw for dredging water up, sort of a helical screw. He basically invented hydrostatics, discovered the notion of density. It's a famous story of him calculating the density of the king's crown to see whether it was made of pure gold or not. The principle of the lever. He, according to some legends, had some kind of mirror system that focused the rays of the sun on enemy ships and set them alight purely by focusing the rays of the sun. Whether that's true or not is debatable. There's also some stories of a huge claw that somehow he managed to construct that would come down onto enemy ships and almost lift them out of the water and destroy them. In terms of his mathematical accomplishments, there are many. He has theorems on pi, essentially forerunners to infinitesimal calculus, which is in the direction of what we're going to talk about today. Theorems on circles, notation for large numbers, and quite a few other things. On his tombstone, he had this result inscribed, that if you have a sphere which is enclosed in a cylinder with a top and a bottom which just encloses the sphere, then the volume of the sphere is 2/3 of the volume of the enclosing cylinder, and also the surface area of the sphere happens to be 2/3 of the area of the enclosing cylinder, if you include the top and the bottom. His gravestone was actually discovered by Cicero. So the Romans took over Sicily at some point, and then a couple hundred years later, Cicero, the famous Roman orator and statesman and writer, was governor of Sicily for a little while, and he actually found Archimedes' tomb and restored it. Such was the great respect that even the Romans had for this man. Even though legend has it that he was actually killed by a Roman soldier after the 2-year siege of Syracuse by the Romans. It was a very unfortunate event. All right, so that's who we're concentrating on today, and we're going to talk about a lovely derivation of his involving geometry, very cleverly used, but elementary geometry, to make a calculus calculation. Perhaps the first real calculation in calculus. To understand and appreciate Archimedes' accomplishment, we should also remind ourselves of a few things about how the Greeks thought about geometry. Their orientation to geometry was quite different from the one that we have now today. So they did not think arithmetically, they really thought geometrically. So a length was to them rather represented by a segment. So this to them was a length. And they didn't think in terms of measuring it via a ruler, they just thought of the segment itself as representing a length. When it came to areas, they thought in terms of rectangles or squares, not numbers. So they might say this area here is the same as this area here. They wouldn't necessarily want to attach a number to the area. So numbers played a secondary role in Greek mathematics, generally speaking, although around the time of Archimedes, things started to change, and Archimedes contributed to an elevation of measurement in mathematics because he was very practically oriented. So to the Greeks, if you had a region like this, determining its area meant not finding a number that represents the area as we would today, but rather finding a rectangular shape which has the same area. So they would look to try to transform this somehow to get the same amount of planar area in a rectangular shape. And since a rectangle is a little bit undetermined in terms of its area, they preferred actually to find a square. That was the optimum thing. To find a square that has the same area as a given shape, that means that you've squared the region. You've determined its area by associating to it a square. So this terminology is a little bit unfamiliar these days. We don't talk about this, but this is what the Greeks meant by squaring something. They meant essentially calculating its area by constructing a square whose area was equal to the one we're looking at. The most famous example of this kind of squaring problem is also another famous problem that we will eventually talk about. It's the squaring a circle problem. And here the problem is to take a circle, a given circle, and construct from that circle a square whose area is the same as that of the circle. So can we find a square with equal area to a given circle? When the Greeks tried to accomplish something like this, they meant by ruler and compass constructions. And many hundreds of years later, the Western European mathematicians were able to prove that this is actually impossible. The Greeks probably suspected this, but they couldn't prove it. So this was a famous unsolved problem in antiquity. However, Archimedes made some progress towards understanding the area of a circle, which is closely associated to this number pi. And the way he did it was by taking a circle and inscribing inside it regular polygons, and circumscribing around it also regular polygons, and then arguing that the area of the circle, whatever that is, had better be between the area of the inner and the outer polygon. So although we may not be able to get at this area exactly, we can at least bound it. He was able to do that. He actually didn't use four-sided ones like this. He used polygons with 96 sides. He was able to make the computation and show that pi had to be between 223 over 71 and 22 over 7. One of the first good approximations to pi. Of course, that was a topic that many subsequent mathematicians took up in years to come. The other important ingredient that we need is the notion of a parabola. And that's a conic section or curve that was of great interest to the ancient Greeks. And Apollonius in particular, whom we've already talked about, was a specialist in the conic sections. But even Archimedes, who came before Apollonius, knew quite a lot about the parabola, as we'll see. So the definition of the parabola that the ancient Greeks used is with relation to a cone. So if you take a point and a circle, and you join the point to all the points in the circle, then you get a cone. And if the circle is sort of directly above the point, then you get what's called a right circular cone. And then if you slice this cone with various planes, you get conic sections. If you slice the plane in this way, you get an ellipse. If you slice it sort of like this, you get a hyperbola. And if you slice it exactly with a plane that's kind of parallel to one of the generators. So in other words, think of a plane that's touching one of the lines of the cone and is parallel to the cone, is like tangential to the cone, and then moving it up, translating it, then that plane will only meet the cone in one branch. There won't be any branch on this side. So it's a very delicate curve poised just between an ellipse and a hyperbola. That's the parabola. And of course there was another definition, the directrix focus definition of the parabola, which is this one here, and that'll be quite important for us. So a parabola can also be defined purely in the plane by the following. You choose a line, L, which is called the directrix, and you choose a point, F, which is called the focus. And then you look at all the points, like this one here, that have the property that their distance to the focus equals the distance to the line. When we say distance to the line, we mean perpendicular distance. So the Greeks didn't use the word distance, they used the idea of length. So they would have rather said that the length of this segment here equals the length of this segment, by which they mean that you could pick this one up and transpose it and put it there, and they would exactly overlap. Now, I have a theory of rational trigonometry, which some of you may know about. It's a kind of reformulation of geometry, where we introduce alternative notations instead of distance and angle. Instead of distance and angle, we have two other notions called quadrants and spread, which are purely algebraic and much better suited for sort of general theoretical work and also practical work in geometry and surveying and engineering problems. Okay, so we won't make a big deal of it here, but I'll just mention that we can describe this condition in terms of quadrants. So the quadrants between P and F is the quadrants between the point P and the line L. And the relationship between quadrants and distance is that if you take the square root of quadrants, you get the distance. Now there's an important consequence of this equality between these two lengths, and that is that if we drop a perpendicular to the line joining this point to F, then that perpendicular splits this in two equal pieces. So this is a midpoint then of that side, which means that these two angles are equal, or better yet in rational trigonometry language, these two spreads are equal. And let me just tell you quickly what a spread is, because it's very easy to state. So the spread, the definition of the spread between these two lines is in terms of a quotient of quadrants. It's the opposite quadrants, this one here, divided by the hypotenuse quadrants. So the quadrants between T and P divided by the quadrants between T and P is this spread. And that's going to be equal to this spread on this side, which is the quadrants from B to F divided by the quadrants from P to F. All right, so this is an important triangle because the Greeks realized that this line here was the tangent to the parabola at the point P. Now these days, many people are familiar with dynamic geometry packages like Geometry Sketchpad or CAR. I've mentioned these before when we were talking about Apollonius' circle problems. And with one of these dynamic geometry packages, you can construct a parabola using this information. So what you do is you construct a line and you construct a point. And then to actually construct the parabola, what you do is you choose an arbitrary point on the line, say T, and you think of this point as being variable. You join T with F and find the midpoint. And then you construct the perpendicular bisector of this side. So we construct that line. And you also construct the line that's perpendicular to L through T. And where these two lines meet, that's going to be a point on the parabola. So as T varies, this point will vary. And most of these dynamic geometry programs have a locus button that allows you to find the curve traversed by a point like this, which is dependent on another point moving. So you can make this construction, and this is the way you can construct a parabola with Geometry Sketchpad or CAR or GeoGebra. Okay, so that's very close to the thinking of the ancient Greeks, and we're going to have to use the geometry that's implicit in this diagram in a major way for Archimedes' insight. All right, so here is famous math problem number 6. It's to find the area of a section of a parabola. Here's the problem. We have a parabola, script P, right there, and we have any two points P and Q on it, and we can join those points forming a chord of the parabola, and that line or that chord will cut off a section of the parabola. That's a little curved part of the parabola, and what we'd like to know is what is the area of that section of the parabola. Now, You might say, well, doesn't it depend on which points P and Q you're using? And that's certainly correct. But what we would like is some kind of expression for the area, some way of computing this area in terms of the position of P and Q. Without calculus, I would say this is a D difficulty 4 or 5 problem. With calculus, maybe it's a D equals 2 or maybe 3, depending on how general you want to be. Archimedes' solution is the following. It's given in terms of an associated triangle. The triangle that you get by taking this chord through P and Q and also considering the two tangents to the parabola at P and Q. So that triangle PQR, where here's R, the meet of these two tangents, is called an Archimedes triangle of the parabola. And here is Archimedes' lovely theorem, that the area of this parabolic section, right here, is 2/3 of the area of the associated Archimedes triangle. So it's exactly 2/3 of the triangle formed by the chord and the two tangents. And it doesn't depend on where P and Q are on the parabola. So you can take any chord, say that one there, form the Archimedes triangle. The area of the section is going to be 2/3 the area of the triangle. It's a lovely, beautiful theorem, and it's a great exercise for you to try to prove this using calculus. I think it's relatively infrequent that students who are studying calculus actually learn this fact. Again, sort of remarkable state of affairs. But with some assumptions, for example, assuming that the parabola is in standard form, maybe like y equals ax squared or something like that, you could probably do this without too much effort if you know some calculus. So that's a good exercise for you to try. And then you can think about how you could prove it for a general parabola. It might be a little bit more challenging in that case. All right, so we want to understand Archimedes' theorem, this one right here. How could Archimedes have proven this 2,000 years or so before the discovery of calculus? So let's have a good, careful look at this proof, because it teaches us quite a lot about the geometry of the parabola at the same time as this area theorem. And it's probably an excellent exercise for you students of mathematics to go through what I'm saying and write it down. So write down the details. I'm going to write down the major points, but I'm not going to write down all the details. I'll just tell you what they are. All right, so we're going to have a look at this diagram and the geometry associated to this chord PQ on this parabola, capital P. All right, here's our directrix, L. Here's our focus, F. And here are the two tangents to the parabola at the points P and Q, meeting at some point R. And notice that this chord PQ does not have to go through the focus. In fact, generally it's not going to go through the focus. Okay, so the first thing that I want to convince you is that this point R is actually the circumcenter of the triangle ABF. And this point A and this point B are obtained by taking the points P and Q and dropping perpendiculars to the directrix from them. Okay, that's where A and B come from. And then we have this triangle formed by these 2 points and F, and we're claiming that this point here is actually the circumcenter of that triangle. In other words, it's the center of the circle that passes through those 3 points. All right, so how can we see that? Well, let's have a look at this tangent here from the point P. And we've already seen in the previous slide that this tangent meets this line AF in a midpoint. So if I make up a little point here, then this and this are equal lengths. That's the property of the tangent construction that we talked about. All right, similarly, this line, this tangent line from Q, will meet the line BF also in a midpoint. So that's going to be a midpoint, meaning that length is the same as that length. All right, now in this triangle ABF that we're interested in here, in this triangle, these two lines that we've just drawn that meet at R are then perpendicular bisectors. Right? They go through the midpoint of the side and they go perpendicularly. Might have said that, right? That's another fact that we know. Those lines are coming perpendicularly down to that segment. So these two are perpendicular bisectors, and any two perpendicular bisectors meet at the circumcenter of the triangle. All right, so what can we do with that? Well, we know that this circumcenter of a triangle is also a point lying on the third perpendicular bisector. So this third side that we haven't talked about also has a perpendicular bisector which passes through R. And I've drawn that there in this blue. So this is also perpendicular as I've drawn there. And it actually goes through the midpoint of AB. So we're using the fact that where the two perpendicular bisectors meet is also the place where the third perpendicular bisector has to meet. So that line there, which is perpendicular to the directrix, must actually be going through the midpoint of AB. So we can say that this side and this side are equal. So these three lines here now are all parallel, and they're all in fact parallel to the axis of the parabola, which is by definition the line through the focus, which is perpendicular to the directrix. Now have a look at these three parallel lines. Okay, they're equally spaced parallel lines. They're equally spaced because along here this length is the same as this length. Now if you have three equally spaced lines, it means that when you look at any transversal is split into two equal pieces by those three parallel lines. So this line here has the property that this side and this side have to be equal. So this point M is actually the midpoint of the side PQ. So we've established an interesting independent theorem about the geometry of a parabola with respect to a chord. And the theorem is that if we have any 2 points P and Q on the parabola, and we look at the intersection R of the tangents, then the line through R parallel to the axis, this one here, bisects the side PQ. Where it meets the chord is actually the midpoint of that chord. So for example, if we took a different chord, say this one here, and P happened to be here and Q happened to be down here, and then we drew the tangents meeting at some point R over here, and then we drew a line parallel to the axis through that R, then we should end up with a point on this chord which is exactly halfway between the two places where the chord meets the parabola. All right, so that's going to be an important ingredient in the geometry that we're going to use. All right, so let's now continue with this proof, moving towards understanding the area of this parabolic segment cut out from the parabola by this chord PQ. And I've drawn again for you the tangent at P and the tangent at Q meeting at the point R. And here is the line through R which is parallel to the axis. I haven't now shown you where the directrix is and the focus. We don't need to concern ourselves with them anymore. We're just going to use the fact that we know that this line that's parallel to this axis meets the side PQ in the midpoint. So we know that this side and this side are equal length. Okay, now we're going to make a few more constructions. And the critical thing is to identify this point here where this line that we've just drawn meets the parabola. Okay, we're going to call that O. And of course that point O depends on the chord PQ that we chose. Now that point O, it's on the parabola, so it also has a tangent. The parabola has a tangent at the point O, and there it is right there. And we're going to let the intersections of this tangent with these two tangents be the points A and B. So we actually have 3 points on the parabola, P, O, and Q. And we have 3 tangents, one at Q, one at O, and one at P. And so let's make the observation that the triangle AOP is also an Archimedes triangle. It's the Archimedes triangle for this chord, because here are the 2 tangents at these 2 points. Similarly, the triangle BOQ, this one here, is also an Archimedes triangle because it's made up of 2 tangents to the parabola. Okay, now I want to prove something to you. I want to convince you that these points A and B are actually midpoints of RP and RQ. And once I do that, that will immediately imply that this line AB is actually parallel to the chord PQ that we started with. So we want to prove that A is a midpoint here. So how are we going to do that? Well, we're going to use the fact that this is an Archimedes triangle. So if we draw a line through this point, which is parallel to the axis in green, then we know that it's going to meet this line in a midpoint. So that side is the same as that side. So that's that same theorem that we identified on the previous slide. So now have a look at this triangle AOP. This is now a midpoint, and this line we know is parallel to this one. So if you think about this triangle here, for example, now, this line is parallel to this one, but this one here is a midpoint of this side. This parallel to this means that this must also be a midpoint of this side. All right? So it's got to be the case that this is equal to this. Exactly the same argument down here shows that this point B has got to be a midpoint between R and Q, and therefore AB is actually parallel to PQ. So we've established this interesting fact now about a section of a parabola. You take any chord of the parabola, you look to see where the tangents meet. If you draw the parallel to the axis through that external meeting point, then first of all, we've already seen that you get a midpoint of the chord you started with, but now we know more. We know that where it meets the parabola, that the tangent there is in fact parallel to the chord that we started with. So we actually have a lot of parallel lines in this situation, which makes talking about areas of triangles quite simple. So for example, the triangle OPQ, which is the triangle here, here, and here, and the triangle RP and Q are easily related. So this line here are parallel, and this is a midpoint and a midpoint. That means this is also equal. Right? This length is the same as this length by similar triangles again. Now that means that the height of this triangle from its base here, the height of the triangle OPQ, is 1/2 the height of the triangle RPQ. This is exactly half of that. And so this area, the area of the triangle OPQ, is exactly 1/2 of the area of the Archimedes triangle RPQ. And as a pleasant consequence of that, the triangle OPQ will be twice the area of the triangle RAB. Why is that? Because the triangle RAB is just a scaled down version of the big triangle RPQ. It's what you get when you shrink by a factor of 2, which reduces area by a factor of 4. So this triangle here has a quarter of the area of the big one. And so this one here, which was half of the area of the big one, is going to be twice the area of RAB. All right, and now at this point here, although we've only been working with triangles, we actually have enough information to be able to see why Archimedes' theorem is true. Let's have a look now at this parabolic arc. All right, going from P through O to Q, we're interested in the area of this section of the parabola. And I want to compare that area with this big triangle. All right, so here's how we think about it. Think about this interior triangle, which is inside the parabolic arc. We've just established that its area is twice this triangle, which lies completely outside the parabolic arc inside our big triangle. So OPQ, we've just established, is twice this one here. All right, that's good. And now let's think about the rest of this figure if we remove this triangle here and we remove the triangle OPQ. What we have left are these two smaller Archimedean triangles, this one here and this one here. And now the same argument is going to apply to them. If we drew, say, a little interior triangle there and an exterior triangle also, then again this interior triangle is going to be twice the area of the exterior one. Similarly down here. So at every stage, the interior triangle that we're removing is twice the area of the exterior triangle that we're removing. And this process keeps on going as we go further and further along. As we go smaller and smaller subdivisions, we keep on taking triangles away, and then we have two more Archimedes triangles to which we do apply the same reasoning. Then altogether, all the stuff that we've taken out at any stage, all these interior triangles that we've taken out, will always be twice as much as the exterior stuff that we've removed. Now in some kind of limit, all of these triangles are going to add up, slowly getting closer and closer to the area of the parabolic arc, the ones that we've taken from the inside, and all the exterior ones are going to add up to the outside. So our conclusion is that the area of the arc will be twice as much as the area outside the arc inside the Archimedean triangle. Because the parabolic arc is just made up of a whole bunch of nested little triangles like this OPQ one. Always having the ratio 2 to 1, and that means finally that the whole parabolic arc to the ratio of the stuff outside it is in the ratio of 2 to 1, which means that that parabolic arc has got to be 2/3 the area of the triangle RPQ. That proof that I just sketched was not exactly Archimedes' proof, but it was very much in the same spirit. That proof that I gave you, I found in this book here, which I'd like to tell you about and recommend highly. It's called 100 Great Problems of Elementary Mathematics and Their History and Solution. And it's by Heinrich Dory, translated by David Anton, and it's available in Dover paperback, so it's quite reasonable. It is, in my view, perhaps the most interesting mathematics book published in the 20th century. Okay, I have the highest regard for this book. It's just page after page of lovely mathematics. And it's a book that I'm going to certainly be drawing on quite a lot in these lectures. Okay, so if you have an interest in mathematics, this is a must to have on your shelf, I think. So I want to also point out how Archimedes actually solved the problem. So it's very much along the same lines, using the same geometry that we've established, but just the argument is slightly different at the end. So here was Archimedes' argument, essentially using the same setup. So let me remind you, we have our points P and Q. We have their intersection of tangents, the point R out here. This line here parallel to the axis, going through the point O. And then we have this smaller triangle OPQ. And to make life simple, let's introduce delta to represent the area of the big Archimedes triangle RPQ. Okay, so everything will be in terms of delta. So in terms of delta there, then the triangle OPQ, because this is half of that, we've seen, that's 1/2 of delta. All right, so Archimedes' idea was, well, let's just sum up all of the triangles inside this parabolic arc. Let's subdivide this parabolic arc into smaller and smaller triangles that more and more approximate the parabolic arc. And we're going to calculate the areas for each one of these little triangles, and then we're going to add them up and see what happens as the number of these triangles gets larger and larger. Basically a fundamental kind of calculus type of argument. Okay, so the first thing to know, we've already got OPQ is 1/2 of delta, that's fine. Now the next triangle on our list will be this triangle OPC, the smaller Archimedean triangle that we obtain by taking the tangent to O, the point A that we've seen before, drawing a line parallel to the axis again, and then maybe obtaining that point C. So that point C is playing the same role as the point O did before, but now with respect to this smaller chord OP. So what is the area of this triangle OPC? Well, it's first of all 1/2 of the triangle OPA. That's exactly the same as the relation between OPQ and PRQ. All right, so this is exactly half of that, for exactly the same reason. So we get 1/2 of OPA. Now we've got OPA. And this one here is half of the triangle OPR. OPR. Okay? Because this triangle here, compared to this triangle, well, you can just think of this base as being extended to twice as much, going to that base there. So the area has gone up by a factor of 2. And so we can now say that it's 1/4 OPR. Now in terms of OPR. And the triangle OPR is 1/2 of MPR. MPR right here. Because we just extend this base to twice as far, and so the triangle that we get has twice the area. So we all together see that this triangle OPC here, this interior triangle, is 1/8 of MPR, and so 1/16 of the whole Archimedes triangle, which we're calling delta. And perhaps more usefully, the relationship between this interior triangle OPQ and this adjacent interior triangle OPC is that OPC is 1/8 of OPQ. Because OPQ was 1/2 of delta, and this one here is 1/16 of delta, so this one is 1/8 of that one. So once we have the relationship between adjacent interior triangles when we're decomposing this parabola, then we can just continue it. So if we know this area here, we know this one is 1/8 of that. And we know the one on the other side is also 1/8 of that. And then the two triangles adjacent to both of those will be each 1/8 of this one here. And that means we can write down an area of the total parabolic section, OPQ, as a sum that keeps on going, that adds more and more terms as we keep on introducing finer and finer little interior triangles. So the first one was the big one, OPQ, which was 1/2 of delta. And then we had these two adjacent ones, the OPC that we just calculated. They were both 1/16 of delta, but there were two of them. So we have to multiply by 2. So we have 2 times delta over 16. And then at the next stage, well, there are going to be 4 triangles adjacent to the 2 ones that we already have. So there's got to be 4. And then we can write down the relationship between this one and this one. So it's 4 delta over 2 8 squared. And then the next one would be 8 over 2 delta 8 cubed, and so on. So Archimedes wrote down this series, and then he realized this is actually just a geometrical series. If we take the 1/2 out, we can see it a little bit more clearly. Then it becomes delta plus 1/4 delta plus 1/4 squared delta, and so on. So it's delta over 2 times 1 plus 1/4 plus 1/4 squared, and so on. And he knew the formula for this geometric series. That it's 1 over 1 minus the ratio, which is 1/4. So this is 1 over 3/4, or altogether 4/3. We multiply that by the half, we get 2/3 of delta. So that's how Archimedes proved that the parabolic area was 2/3 the area of the bounding tangential triangle. It is really a kind of a calculus type computation. So the debate between the English and the Germans about whether Newton or Leibniz invented calculus, it has to be taken with a bit of grain of salt, I think. Archimedes really had a good part of the calculus already in his mind, in some level at least. So that was Archimedes. We're going to see him more in this series, naturally, and so we'll look forward to some more interesting problems associated with that great mind. In our next talk, we're going to change gears a little bit and do something a little bit different. We're going to talk about a famous problem which is still debated today. It's a paradox that's associated to the name Newcomb. It's called Newcomb's paradox, and it was popularized by Martin Gardner in his famous Scientific American Mathematical Games column. It's a problem that has to do with free will and has to do with prisoner's dilemma, kind of game theoretical discussion. I think you'll find it quite interesting. All right, so I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.